Good morning, students. I'm teacher Betty, continuing with the advanced inorganic topics, lesson 9. In lesson 8, we looked at inorganic polymers containing phosphorus. Today, we are going to look at stabilization of oxidation states of transition metal elements. With the exception of a few, most of the D block elements show more than one oxidation state. Reason why they show several oxidation states there are mainly two reasons. The first reason is N-1 bracket D and NS orbitals in the atoms of the D block element have almost the same energies. And electrons can be removed from N-1 D orbitals as easily as they can be removed from the NS orbitals. The second reason is after removing NS electrons, the core becomes unstable and it can lose one or more electrons, resulting in the formation of cations having different oxidation states. That is to say, the removal of one or more electrons from the unstable core gives several oxidation states to transitional metals. Stabilization of unstable oxidation states. Compounds are regarded as stable if they exist at room temperature, are not oxidized by air, are not hydrolyzed by water vapor, and do not disproportionate or decompose at normal temperatures. Within each of the transitional groups, there is a difference in stability of various oxidation states that exist. Factors affecting the stability of the oxidation states. There are mainly three factors. The first one is the type of the ligand. The second one is the crystal field stabilization energy. And the last one is the lattice stabilization energy. How does the type of a ligand stabilize the oxidation state of transitional metal? It may be seen that the low oxidation state like -1, 0, or +1 are unstable. These states are stabilized by forming complexes with pi acid ligands like carbon monoxide, nitrogen monoxide, ethylene, benzene, and others. These ligands are electron deficient. They have vacant pi orbitals, call them vacant pi acceptors, in addition to the field orbitals or the donor orbitals. The donor orbitals on the ligand overlaps with the vacant orbital on the transition metal atom in the low oxidation state, and it forms a ligand metal sigma bond. The formation of the sigma bond accumulates a negative charge onto the transitional metal atom, and the ligand receives a back donated electrons from the field D orbitals of the transition metal, resulting into the stabilization of the lower oxidation state of the metal atom. The higher oxidation state can be stabilized by forming complexes with small, highly electronegative ligands like the fluoride, the chloride, and others. Since these ligands provide the bonding electrons to be wholly attracted to the metal ion. The second factor is crystal field stabilization energy. According to the crystal field theory, the bonding between the metal cation and the ligand is not covalent, but regarded as purely electrostatic between positively charged cation and negatively charged anion, or dipole molecules, which act as a neutral ligand, for example, water, ammonia, and others. Complexes are formed when centrally situated cation electrically attract ligands, which may be ions or dipole molecules. So the higher the crystal field stabilization energy, the stable the complex formed. Then the last factor is lattice energy. When a larger number of cations and anions are brought nearer to each other to form ionic crystal, they arrange themselves in a regular pattern to attain a close-packed type structure. In this process of attaining this type of structure, energy is released, and hence the system gets stabilized. An assignment I can leave you with is what is meant by crystal field stabilization energy. Another one is explain, giving appropriate reason, why hexaamine cobalt 3 ion is more stable than the hexaamine cobalt 2 ion, while the hexa-aqua cobalt 3 is less stable than the hexa-aqua cobalt 2 ion. The last topic is group 18, or the zero group element. The assignment I can give under this topic is give 5 reasons why are the layer gases chemically inert. Describe a chemical method that can be used to isolate inert gas mixtures from air. Include the equations in your description. Number 3, by use of Dewey's coconut charcoal method, describe how layer gases can be separated from each other. Number 4, list any 2 uses of the following noble gases: helium, neon, argon, krypton, xenon, and radon. Then number 5, write equations to show how each of the 3 stable fluoride forms of xenon are hydrolyzed in water. Then the last one is draw and name the structure of each of the 3 stable fluoride forms of hexanon. So this has marked the end of advanced inorganic topics.